Swayam Prabha. Digital India. Educated India.
So welcome back. In the previous slide and the short movie, what you see is that we have different material, either we can say the different sites. One was rocky, another was of soft sediments, and then we are having in water saturated sediments. So effect of the seismic wave which passed through this area, rocky, soft and water saturated, so they will behave differently, and the amplification, the effect of that seismic wave will be different at different point. Now in the previous lecture which I was showing that why it is so important to map the active fault on the surface, that is the surface rupture, is that without having the understanding, one should not put the house right on the top of the fault scarp or the fault line, otherwise you can experience an total damage if there is a rupture. Of course, in the epicentral area the peak ground extension will be extremely high, and along with that, if you know the line of surface rupture or the fault line, you need to avoid putting your structure on top of that. So amplification will vary from place to place, and as we were talking about, that if you have the loose sediments mostly closer to the river valleys or the alluvial plains or the flood plains, you may experience a severe liquefaction phenomena. So seismic shaking, amplification and duration. This is an example from Mexico. The concern was mostly about the population, because most of the populations, the settlements we will come across will be in the alluvial plains because of several reasons, for the water resource and also for the fertile land and all that. So large portion of the Mexican city sits on the bed of Lake Texaco since European settlements way back in 520 AD. The area provides flat terrain. This is one reason which I was talking. Fertile soil, ideal for the settlement. So any settlement, even if you go back and try to look at the Indus Valley civilization, most of the sites were along the adjacent to the riverbed, and this is one of the reason. Even today, you will see a thick population is in the Indo-Gangetic plain because of the flat terrain, fertile land, water is easily available. So people, of course, have more try to settle down in such areas. But this terrain and thick lake deposit lead to one, amplification of the seismic wave, and extended the duration of the seismic shaking from the earthquakes. So this is another added problems which we will experience, and usually people experience if they are in the alluvial plain areas. So one will be amplification. Second, because of the amplification, you will see more the duration of the shaking will increase. So this example, if you look at from the effect of seismic energy amplified due to 1985 earthquake, having its epicenter located about 400 kilometers away from the Mexican city. So Mexican city is located here, and this is a schematic diagram. The earthquake was triggered somewhere here, epicenter, which was almost 400 kilometers. So what would have been expected is that in the epicenter area, maximum damage should have occurred, and the duration would have been larger here, but that did not happen. The amplification was comparatively higher, 400 kilometers away from the epicentral area, that is in the maximum city. And the reason was what we were talking about in the previous one, that the whole city or the settlement is sitting on the lake deposit, and the duration was also much higher as compared to what was experienced in the epicentral area. Whereas in between, in some regions, the peak ground acceleration was comparatively lesser, but even of 400 kilometers the peak ground acceleration was much higher. So the important part is how far we are sitting will be one criteria, of course, but what are the deposits, underlying deposit, that will be the most important parameter one should understand. So if you are sitting on the hard rock, of course you are to some extent safe, you will not experience the amplification. But if you are sitting on softer material, or your buildings are sitting on the softer material, even though you are sitting away from the epicentral area, you are bound to experience peak ground acceleration will be much higher. Now this is another example which will clear your understanding about the seismic shaking. So change in the field loading conditions, as the energy, that is a seismic wave, propagates towards the surface upward from the hypocenter. Okay. It changes, and slowly what happens is that over the time you will have the deformation because of the cyclic stress. So this will go back and forth, and that will result into your increase in pore water pressure, complete compaction of the water saturated deposits or the material. Now here rho prime is your, or sigma prime is your initial effective stress, vertical overburden, and tau is your horizontal cyclic shear stress. So if duration is much higher, then the effect will be much higher. So loosely packed deposits will have larger pores filled up with water, but yes, of course, this should be water saturated. If it is not water saturated, then chances are less to enter into the liquefaction phenomena. So near the surface, if you are having unliquefied layers like clay, and then or the fine silty sand, but 2 meters you are having porous deposits like sand, cohesionless, saturated with water, that will result into the liquefaction. So liquefaction usually take place where the sediments are cohesionless, are completely saturated. It depends on the relationship of the cyclic shear stresses developed by earthquake shaking and the amount of stress required to trigger the liquefaction. Depth of the occurrence of liquefaction varies from few meters up to tens of meters. Okay. But below this, up to 10 meter, if you are having, like, chances are a bit less, but of course you will have the liquefaction will not reach right up to the surface, it will within the subsurface layers because of the overburden, but below that you will not be able to experience much of the liquefaction. Development of liquefaction is highly difficult at greater depth. The reason is because of increase in normal static effective stress, which will increase the resistance of the sediments to shear or deform, because it will be difficult to shear the material which is sitting at the greater depth. So what we see here is the schematic diagram which talks about the non-liquefiable layer with low permeability, and this is a porous layer or the liquefied layer, mostly the cohesionless, scent but water saturated. So when the cyclic shear affect the sediment package here, will result into increase in pore water pressure, and this liquefied material will be poured out through either through conduit in a form of sand blow, and this phenomena is very much similar to what we see in the volcanic eruptions. Now sometime it has been also seen, because for if we need to do the seismic microzonation, then we try to take number of boreholes and then we study the stratigraphy, and we also try to understand that how thick is this unit, that is the unit which will be prone to liquefaction and which is a non-liquefiable unit. So this is your H1 and this is your H2. So this also will be, if this is very thick, then you need more of the peak ground exudation to break this unit. If this is thin, then even with the lesser ground shaking, you will be able to experience the liquefaction. And the threshold limit to trigger the liquefaction is with an earthquake of magnitude 5.5. if you have, then it is quite likely that you will experience a liquefaction. If a site is idle, then ideal site is what we have discussed is that we should have an cohesive less sediments, B you have like water saturated, and then C you should have an capping of non-liquefiable unit, that is your H1, and this one will be your H2. So this is an ideal condition which we should have, and even with the magnitude of 5.5 you will be able to trigger the liquefaction. These are few examples which talks about that how the paleoliquefaction or the liquefaction which took place or triggered by the previous earthquakes will look like. So this is again a section, as we were looking at the sections of faulting events or the ruptures along the active fault. This is the similar to that, but this is for liquefaction. Now these are the craters which have been formed, and these are the conduit which broke these units, and they have brought the material from subsurface. And when such depressions are been created on the surface because of the strong ground shaking, then some point of time you see also the deposition which is taken, because it is a depression, so material will come into the depression and will get deposited. But one interesting thing which you should mark here is that when the material with the high pore pressure moves up through the conduit, it breaks this unit, because it is coming up here. So what you see here is the broken, disoriented fragments of layer 1 or sorry the unit C. So in this the broken fragments have been seen disoriented. So this we say the rip-up class. So we are having a class which have been broken from the overlying units when the material or the liquefiable material is moving towards the surface. This also helps us in identifying that this conduit is the feeder dike for the feeder conduit for the liquefiable material coming right up to the surface. Even if you are having the liquefaction taking place in the deeper part, and they may not reach right up to the surface, but they die out getting liquefied material, like it gets along these sedimentary layers, which we call sills. So this is an example of liquefaction from Andaman, where you can I'll show in one slide. So we exposed the sediment succession in Andaman after 2004 Andaman Sumatra earthquake, and looking for the tsunami deposits, but we came across very beautiful liquefaction features also. So here you see the class sitting in this clayey bed. So this is a class which I was showing, it's similar to the conduits, and this is a dike which is coming up, very beautiful one. So this is the source unit, and this is a conduit which is coming up and depositing. So this is a very small scale crater and or the sand blow which was been formed because of the previous earthquake, but this was not related to 2004 Sumatra Andaman, but this is an older event by older earthquake which resulted into the or caused the liquefaction in this region. Similarly, you can see the clast here of this same clay bed, and this is the sand which was been poured out because of the strong ground shaking. Again, this is not related to the 2004, but in the previous large magnitude earthquake in this region. Surface manifestation of liquefaction features, what we saw from the SETTLE radar topographic mission data in just after the 2001 Bhuj earthquake. In most of the areas which was water saturated or near surface water saturated sediments were available or the units were available, we saw that the water was being poured out in the Great Run of Kutch, and many people started talking about that the ancient dry bed of Saraswati is now revived because of this water coming right up to the surface, but this was a temporary phenomena, this was not a permanent phenomena. And as I discussed, that there will be a strong ground shaking, and the material, the porous material which are saturated will be compacted, and because of the high pore water pressure, the water will be almost ejected out on the surface. So I'll stop here, and we'll continue in the next lecture, trying to see more signatures of the liquefaction. And as I told, that this is a very important part. Of course, we need to know that what type of material on which our construction has been done and how far we are sitting from the source. Thank you so much.